The following content is created by DrAvitech. Your support and donation will help me continue to offer high-quality educational resources for free. To make a donation, send an email to 6drcyril@gmail.com or comment donations below.
Welcome guys, I'm DrAvitech, and in this video, we're going to be explaining even and odd functions algebraically and graphically, so you understand how it might be easier to solve Fourier series problem. You might be wondering sometimes it is stressful to find all coefficients. It is stressful to find the 3 coefficients in Fourier series. Well, sometimes for some kind of problems, you can actually find it much more easier to get your Fourier series coefficients. Well, let's start with algebraically. Let us start with algebraically because most persons might need that. So let's start with algebraically. Now, for me to know an even function algebraically, I think I should write this algebraically. So let's start with this one. So algebraically, please take note that this part might not really be necessary when it comes to Fourier. But it's important you know this because there's an application there. So algebraically, if f of x is the same as f of minus x, then the function is even. The function is even. Now, what does this tell me? This tells me that if there's a function somewhere, that's if I should put a negative number into that very function, if I should pick an input to that very function, the answer we get is the same as when I give it a positive input of the same number. Let us do it this way. So let's say that f of x is equal to s squared, for example. Let's say f of s is equal to x squared. Now, let's pick in 2 numbers. Let us check if when I put in f of 1, and put in f of minus 1, let us see if it's going to be the same. Let's see. So first of all, okay, let me even use 2. Sorry, I think 1 does not mix. Let me use 2. So let's see f of 2. Anywhere I see x, I'm basically going to be putting 2. So this will be 2 squared. So this will then become 2 squared is 4. So you can see that f of 2 gives us what? Gives us 4. Now the next one again, let's go. F of x is s squared. Now f of minus 2, let's see what minus 2 would be. So what will happen here? This will then become minus 2 all squared. Minus 2 all squared is positive 4. Now, as you can see, f of 2 and f of minus 2 gives us the same value. So for even functions, even if you take a negative number, the function is still the same. It's still the same. So for s squared, for example, if you make the x value become negative, the function will still be the same because it is an even function. So in your exam, if they should tell you a function is even if dash, a function is even if f of s is equal to f of minus x. Or you could say if f of minus s is equal to f of x. I think some persons turn it around. It's still the same thing. But that is the condition, algebraic conditions, if 2 functions are even. Now, another way to look at this, let's say we have a function. So this is A. Let's look at B. So let's say a function f of x is equal s squared plus 4x to the power of 4 minus s to the power of 6. Would this function be an even function? Now, I don't really want to stress myself. I don't want to use numbers because using numbers will seem so funny. So let's use x. But this time around, let's see what f of minus x would be. So the first one is x, right? Positive. Let's see if when I put the x as negative, if my answer will still be the same. So let's try that out. So this is x, right? All of the x will become negative. So minus x squared plus 4 into minus x to the power of 4 minus x to the power of 6. Now, one thing you need to remember is whenever you're dealing with numbers, if you take an even power, your answer is always going to be positive for all real numbers. If you take the square, you take the fourth root, you take the sixth root, your answer will always be positive. So in this case, minus x to the power of 2 will give us s squared. Because minus x all to the power of 2 actually means minus x times minus x. So minus times minus is plus, x times x is s squared. So that's why it's that. And then plus 4 minus s to the power of 4 is still the same thing as s to the power of 4 because the negative will still be positive since our power is even. Then this is minus s to the power of 6 will give us s to the power of 6. Now what does that mean? That means that after putting minus wherever x is, it's still the same way we do it when it's just x. So the function is even. So this is what it means that algebraically a function is what? Even. Now how about when a function is odd? So number two. Let's take a look at number 2. So for number 2, okay. If f of minus x is equal to minus f of x, then the function is odd. Then the function is odd. Now as you can see, for odd functions, it's like the minus is coming outside. So if you have f of minus x, is the same thing as when you bring out the minus, so minus f of x. So this is the algebraic condition for odd functions. Now let us use one example. So f of x, let f of s be equal to, let's say x to the power of 3. So we have x to the power of 3. Now let's see, we're going to pick a positive number and pick a negative of that same number. Let's see how the answer would look. So let's say we want to see f of 4 and f of minus 4. Let's see what it will be. So first of all, f of 4. This means we're going to be having 4 cubed. So 4 cubed is 4 times 4 times 4. So that's 64. So you see that we had positive 64. All right. Next one. So f of x is s cubed. Now let's see what f of minus 4 would be. When we pick a negative. Since the 4 is positive here, let's pick the negative. So anywhere I say x, this will be minus 4 cubed. So this is minus 4 times minus 4 times minus 4. Minus times minus is plus. Plus times minus is minus. 4 times 4 is 16. 16 times 4 is 64. Now you can kind of see that something happened here. This, when it's positive, it will be positive here. When it's negative, it's negative. So here's the thing. If you look at this carefully, what's going to happen is we're going to say that f of 4, we notice that f of 4 was supposed to be the same thing as f of minus 4. Yeah, realistically, f of 4 is supposed to be the same as f of minus 4. But we notice that it's not the same because f of 4 was 64. F of minus 4 is minus 64. So that means that there's a minus outside. So you can write it either ways. There's a minus outside. Is that okay? So there's a minus outside. So this is what it means. So when you pick f of minus x, it's the same thing as minus f of x. It's like the minus is coming outside. So in this case, when the minus comes outside, you're going to have it here. Remember I said these two places can be interchanged. All right. So this is what we have. Now see, here's the thing. A sum of all odd functions is going to be odd, and a sum of all even functions is going to be even. Take a look at this example. S to the power of 6, s to the power of 2 on its own is even. S to the power of 4 is also even. S to the power of 6 is also even. A sum of all of them, or a difference of all of them, will still remain even. So a sum or a difference of even functions will be even. A sum or difference of odd functions would also be what? Odd. So that one is not a problem. So when it comes to the sum, it is still the same. There's no issue with that. It's still going to be what? The same. However, if you should have a sum, I think let me write this down. Number 2, well, number 3. Number 3, the sum or difference of odd numbers, of odd functions is also an odd function. So that's number 3. Number 4, the sum or difference of even functions is also an even function. So I believe that one is quite kind of clear because I've already explained it using something like this. I've already explained it using that. So the sum is not really our problem. The sum is not really our problem. Now take note, if you sum an even function and sum an odd function, the function is neither even nor odd. If you sum a function that is even with the one that is odd, the function is neither even nor odd. So take note of that. So the sum of an odd and even function is neither even nor odd. Now let's see. So let's say f of x is equal s squared minus s cubed. Let's say it's equal to something like this, s squared minus s cubed. Then let's pick a number. Let's say f of 3. So let's see how f of 3 and f of minus 3 would behave. Let's see how they will behave. So let's start with f of 3. So for f of 3, anywhere you see s, you're going to be putting 3. So this will be 3 squared minus 3 cubed. Now 3 squared is 9. 3 cubed is 27. When you subtract this, you're going to have minus 18. So this is f3. Again, the function is f of x equal s squared minus s cubed. Now let's pick f of minus 3. So since we've done the positive, let's do the negative. Now, anywhere I see x, I'm going to call it minus 3. So this is x, and this will be minus 3 squared minus, this is x again, so that's minus 3 cubed. Now, minus 3 squared, because this is raised to the power of 2, minus 3 times minus 3 is plus 9. And then this is minus 3 cubed is minus 27. So this will be 9 plus 27. So right now this will be 36. Now as you can see, the answers are totally different from each other. Unlike previously where we know that, okay, the answers are kind of the same, but maybe there's a multiple. For example, these answers now, they were almost the same, just that they multiply this one by minus. Why for even function, you have exactly the same answer. For even functions, you have exactly the same answer. For odd function, one will be the negative of the other. But this one, they're not even the same to even start with. So you can see that when you have a sum of an odd or an even function, what you're going to be having is neither even nor odd. Neither even nor odd. That's what you're going to be getting. Now let's talk about products. So let's talk about products at 6. Products. Let's talk about products. Now, here's the thing about products. Here's the thing about, since we're dealing with algebraic, here's the thing about products. It's a very funny one. Let me call this I. Even when an even function multiplies another even function, the resulting function is also even. When an even function multiplies another even function, the resulting function is also even. All right. The second one is going to be funny. When an odd function multiplies an odd function, the resulting function is even. My God. Yeah, the resulting function is going to be even. Now let me show you why. Let's pick s cubed as the first odd function. Let's pick x to the power of 5 as an odd function. I believe you know by now that when it comes to just a single number, just a single variable x, if the power is even, then the function is even. As you can see, s to the power of 2 here is even, so that means s squared is even. S to the power of 2 is, the squared here is even, so s squared is even. 4 here is even, so s to the power of 4 is even. 6 is even, so s to the power of 6 is even. Now for an odd function, you will notice that if the power is odd, that means s cubed is going to be also what? Odd. So that's what I mean here. So if you look at these two guys, they're going to be odd functions because their powers are odd. But remember that if you should multiply two things that have the same base, what do? You add up the powers. So this will be x, you then say 3 plus what? 5. So this is x to the power of 8 because 3 plus 5 is 8. Now, you can see that this is now even because 8 is an even power. So s to the power of 8 will be even. Beautiful. So right now, this means that when an odd function multiplies another odd function, your result will be even. The result will be what? Even. Very beautiful thing. So you can just write it somewhere that x to the power of n is even if n is even. Then x to the power of n is odd if n is odd. So this is it. This is just it. So we have an even function. Let's proceed. I want to wipe this guy out. Number 3. An even function multiplied by an odd function would give us an odd function. This thing wants to look like maybe a logarithm. Where, it doesn't even look like that. If you have an even function s squared multiplying an odd function s cubed, this will now become x. You know you are multiplying the same base, so you need to add the power. 2 plus 3 will give you 5. So that's why it's odd. So you can see that an even function times an odd function will give you an odd function, s to the power of 5. Next, an odd function multiplied by an even function is also odd. So if you have odd function, let's say x is an odd function, you multiply that by s to the power of 5. No, these two are odd. S to the power of 4, for example. So this x here is raised to the power of 1, so it's an odd function. This s here is raised to the power of 4, so it's an even function. And this will be x. 1 plus 4 is 5. So that's odd. So this, you need to take note of this. It is very, very important. So this is number 7. This number 7. Now, with this, I've been able to algebraically explain Fourier. I've been able to explain algebraically what even and odd functions are or what they look like. And let's talk about the graphical nature of them. Graphically. So for graphically, the first thing I want to do, should I call it number 1 or number 8? Any of them, it all depends. So graphically, the first thing you want to know about even functions is a function is even if it is symmetric, if it is, I can roll a line with there when I get there. If it is symmetric at the y-axis, So let me explain what that means. Now, to be symmetric kind of means to be equivalent or to be equal. It kind of means any of them. To be equal or to be the same. So symmetry is just saying, okay, let me say symmetry of a shape, geometry, for example. When you look at this board, is there a way you can put a line somewhere? And when you put that line, this board will be divided into 2 equal parts. Yeah, there is. Not just 2 equal parts, but 2 equal parts that can close or fold themselves in exactly the same way, shape, and form. Yes, there is. Because if you can measure this and get the midpoints, when you cut it at the middle, these 2 parts will now be the same, where they can both overlap each other. So be very careful, they have to overlap. Now, for this one, if the function is even, it is symmetric at the y-axis, or you can say about the y-axis. What it means is, the y-axis is that line. Is that line that makes this part to be equal to this part. So let me explain better. So this is the line, this is the y-axis, then this is your x-axis. If I have a function that looks like this, for example, let me first of all wipe this part out so that it wouldn't start confusing you. Let me wipe this part out. Now, if I draw this very well, hold on. So let's say I have something like this. Now, if I draw this very well, what would you notice? You will notice that if let me say I'm standing in a mirror, exactly. I'm standing in a mirror. The y-axis is acting like a mirror. So what is between me, the mirror, and the object, the image, sorry, because I'm the object. So I am the object, the mirror is in between, then there's a reflection. So me, I am the object. The image inside of the mirror, this is the image. So this is the image. This is the object. So the y-axis is like a mirror. So anything you see on this side is exactly the same on the other side. So it's like a reflection. It's like a reflection. Take a look at this again. Take a look at this again. Imagine if I have something like this. Imagine if I have something like this. You notice that this part is looking like this part. And they are on the y-axis. If you kind of take a paper and you overlap them together, this function will be an even function. Let me see if I can make an example. Can I really? This might be looking very small. Okay, let's see. This is very, very fun. I don't think I want to do this. So this is my function, for example. This is my function, for example. This is my y line. If I should fold it here, if I should fold this thing here, would you fold, young man? If I should fold it here, this part, every single box would align. So this line where it aligns, this line is the y-axis. So this line is the y-axis. So that it closes perfectly. Now this function will be called an even function because every single thing is mirrored on the other side. Currently it's raining. I don't think I can continue this video because the rain will be disturbing me. So let's hold on for some time. Let's proceed. So as you can see, this is what an even function is. Now take a look at another diagram. Take a look at another diagram. Oh, that's why. This is also an even function. Even though my line is not straight. Hold on. So I have this guy. Okay. Okay, so looking at this is also an even function, because even functions, they are symmetric at the y-axis. So it means at the y-axis, what is on this side is equal to what's on this side, and they can both overlap on each other. They can both overlap. Or you could even say that at the y-axis there's a reflection. There's a reflection. So most times you try your best to see if you can go and pretend as if you're a function and you're standing in front of a mirror. Yeah, you can do that. So you pretend as if this line here is a function. Pretend as if you are a function, then the line is a mirror. So if this is you, how would the reflection of you be on the other side of the mirror? So that is what even function is. Now let me give another diagram of even functions. This is another diagram. Let's see. Do you know that this is also an even function? This is also even because this side is perfectly fitting this very side. Then this side is also perfectly fitting this side, in such a way that if you use a knife and you slice the y-axis, these two parts will perfectly lap on each other. Every single corresponding point will lap on each other. So this is also an even function. Now this here is also an even function. Even though I didn't draw that very well, but this is also an even function. If you should slice it at this very point, what is on this side and what's on this side, they can perfectly overlap on each other. So every single thing here, these are all even functions. They are symmetric at the what? At the y-axis. They are symmetric at the y-axis. Now let's see the second one. Let's see the second one. Number 2. A function is odd if it is symmetric about the origin. Symmetric about the origin. So this time around, it is the origin. It is the origin that is the mirror. Yeah, you can call it like that. Let me wipe this part of the board. If you're enjoying this video, give it a like, comment, say something. So number 2, a function is odd if it is symmetric about the origin. Now sometimes I don't really like stressing myself about this. Here's what I do. Here's one beautiful thing I do. If a function is on opposite quadrants, that's how I answer this question when it comes to number 2. So maybe a function is even or odd. If that function, if that graph is looking as if the numbers I have are on 2 opposite quadrants, I will say that they are odd functions. Take a look at this graph. Take a look at this graph. So this is what I have. Now see, this is a straight line. This right here is a straight line. Now this is the origin. This is the origin. This function is going to be an odd function. This function you see here is actually an odd function. So we say that this is symmetric at the origin. It is having its symmetry at the origin. Now, if you do not get this, here's how I get my answer. Every single function, every single graph we have, we normally know this is the first quadrant, this is the second quadrant, this is the third quadrant, this is the fourth quadrant. Now here's the thing, here's what I use. If a function has a graph at the first and a graph at the third, that is 2 opposite quadrants, then that function is odd. If you look here now, what is at this place? The line here is exactly the same with the line here. So these two guys are befitting first and third. So it's going to be an odd function. Or if it is having second and fourth, it's going to be an odd function. So take note of that. Look at this other diagram. This one can just be called line X because this is a linear line. Take a look at this. Don't know why my graphs are not straight. Okay, something like this. Yeah, I don't really know why my graphs are not straight. But yeah, something like this. The same thing also. The same thing also. So this right here, there's something here, and then we have something here too. So this is first, and this is what? This is third. this is going to be an odd function. Let's proceed. There are better examples so you kind of know what to do when you have different problems. And take a look at this one. We have something like this, and then something like this here. This would also be an odd function. This would also be an odd function. Because if you slice it at the origin, if you put a line here and slice it, these two will perfectly cover each other. But like I said, if that's not a good picture for you to understand, you can just say, oh, since this one is at the second, this one is at the third, then definitely it must be an odd function because they are on two opposite quadrants. So that's one way to know your answer. That's one way to know your answer. Hold on, let me put lines here, lines here. Yeah, so whatever is here and here are the same. So you can kind of, I believe you're not getting the picture in a way. Look at this other one. Look at this other one. I have a line like this, and I have another one like this. This would also be an odd function. This is also odd, because what I have here and what I have here, they are exactly the same on two opposite quadrants. Two opposite quadrants. Now, another thing to look at, let us say we have something like this. This is also what? This is also an odd function. In fact, this is not just only, or this is the graph of sine x. It's not just, or this is the graph of sine x. Even though it continues just like that, but this is the graph of what? This is the graph of sine x. This is an odd function. So if you graph sine x, this is what sine x looks like. And if you graph cosine x, it's kind of looking like this. Yeah, it's kind of looking like that. That's what it looks like. Yeah. So you can see that this is also even. This is also even because this, when you look at these first two parts here, if you have a mirror, if this your line is a mirror, if you put this thing in front of it, the reflection will be this. Then this one, the reflection would also be this. And remember, in mirrors, you maintain the same distance. I don't really know if it's a fake mirror or real mirror, but in a mirror, the distance will still be the same inside the mirror. So this is your sine x. This is your sine x. You notice that what I have here is at the first, and I have something that looks like it at the second. So they're just like mirrored images. This would be like a 180-degree rotation. Yeah, that's what this would be. But let us proceed. So this is how your even and odd function looks graphically. This is how your even and odd function looks. This one, this is, I can call this minus s squared. This minus s squared because, yeah, the parabola is facing that way. This would be s squared, even though I didn't put it at the origin. And this is cosine of x. So this is how your graph, if you notice that your graph looks like any of this, you then know if it's even or if it's odd. Now, so the main deal, how does all of this make Fourier series easier? How does it make it easy for us? If I know a function is even, what can I do with it? Does it even make life easy, or it even makes things complicated? Now, please take note that some functions are neither even nor odd. If a function, because I've already stated it here, algebraically, that when the sum of an odd and an even function, this one is going to be neither. Now, when it comes to graph, if it does not befit this and does not exactly befit this, then it is neither even nor odd. If the function does not look like this, does not look like this, it is never, it is neither even, neither is it odd. Now let us see how this applies to Fourier. Let's see how it applies because we need it. It has been complicated, it has been tiring, it is a difficult task. You know, it's a stressful task for us to find all of the three coefficients. It is actually stressful for us to find all three coefficients. So there are times where if you know a function is even, things can be much more easier. Let us get started with even functions. To start with, everything I want to say currently will not, I repeat, will not be true if the interval is not symmetric. So condition one, which is very, very important, you cannot use this to simplify Fourier if the interval is not symmetric. So the first one, the interval must be symmetric. because we're dealing with symmetry here. So the interval must be symmetric. So it must be from minus pi to pi, or minus L to L. Symmetric. So if you have a graph here, this is pi, okay, this is minus pi, this is pi, then you have 0. To be symmetric means there's going to be a middle where the distance from this part and this part are equal. So 0 to minus pi and 0 to pi are the same. That's what it means by symmetric. But if you have 0 to 2 pi, it's no longer symmetric. Yeah. So we don't define it like this. So this is what we mean by symmetric. We don't use this one. So let's proceed. So this is condition 1. If this one no work, just know that it's not going to work. Just this is the first one. Because most persons confuse this. This is s squared. Okay, yeah. I know this is not come down very well, but this is s squared. S squared is even from the graph. Good. Now, does it mean that we can now apply it to simplify functions, to simplify my Fourier series, if it is not symmetric? No. If the interval is not symmetric, the simplifications I am about to list out cannot work. So these simplifications would work if and only if these intervals are symmetric. Let's say if and only if. Yeah. So that's it. So number 2, let's talk about even functions. Even functions. So I'm going to be going back to this graph to reference it. So the first part, a naught. On a normal day, the formula for a naught is 1 over pi integral from minus pi to pi of f of x dx. Now let's come back to this function. Let me use this one as an example. So you understand why this will simplify my Fourier series. Now, this expression I have here, if a function is even, we're integrating from minus pi to pi. So let me say this is minus pi, and then the middle is 0. What I notice is integrals are all about areas. In fact, we use integration to find areas, so it's all about areas. Now, one thing I can know or be sure is the area above the x-axis is always positive. Now, if this is symmetric, meaning what is here is equal to what is here, that means if the area I have here is plus a, the area I have here will still be plus a. So what it means is the sum of these two areas will be double of one part of it. It's going to be double of one part of it. Please listen attentively. I said that this area is the same with this, because this box, this rectangle here, from 0 to pi, is the same with the rectangle from 0 to minus pi. So instead of integrating from minus pi to pi, which might be bulky, instead of integrating from minus pi to pi, why not only integrate from 0 to pi? Only integrate from 0 to pi. Then you multiply by 2. Because if you know that the integral from 0 to pi is a, all I have to do to get the full area is just times by 2. Because to get the full area is the double of 1. I believe you get the picture using this very graph. So let's come back here. So this, our integral, will then become something like this. We're going to say this is 2 times 1 over pi. Instead of doing the integral from minus pi to pi, we're going to do 0 to pi. And then f of x dx. Now this will then become 2 over pi integral from 0 to pi of f of x dx. Now this expression you see here is a simplified version of the answer. So this answer is actually simplified. Do you know why? Instead of you integrating from minus pi to pi, you're now integrating from 0 to pi. So your workload is much more easier because you have reduced your limit of integration. Back to the graph again. Let me explain. 0 to pi, you integrate this part, you get only 1a. But to get the full area, because this part is exactly equal to this part, just times it by 2. So that's why this 2 is here. So this is your formula. So this is a naught. So we call this a simplified version of A naught. This is your A naught. Now next, let's find A sub n. A sub n. I kind of need space for this. Okay, now I know that this is 1 over pi integral from minus pi to pi of f of s cos nx dx. So this is what we have. That is the formula for A sub n. Now let's come back. This time around, let me use this very graph. The first thing you want to ask yourself is, integrals talk about areas. Now imagine if you have an even function, because we agree that we're dealing with even functions, so f of s is even. F of s is even, cosine of s is even. Listen up, please. F of s is even, cosine of s is also even. If we should multiply these two, you will still have an even function, because an even function times another even function is even. Remember I told you that cosine is even because this is the graph for cosine. Cosine is even because it's symmetric at the y-axis. So if you multiply a function that is even with another function that is even, then everything will be what? Even. And we've said it before that if you have an even graph, this is what it looks like. This is what it looks like. So since everything here is even, it's going to be looking like this one also, where I will say this is 2 over pi integral from 0 to pi of f of s cos nx dx, because it's just the same as saying that we're just doing this. So instead of explaining again, making the video longer, this will just be your answer. You use 2 to multiply because I'm using this one now. Since the function is even, meaning it can be modeled as something like this. It can be modeled as something like this. So this is your minus pi. This is your pi. This is 0. Now, we know that this part and this part are exactly the same. Instead of finding the full area in integration, let's first of all find only this part. Let's first of all find only this part. The area from 0 to pi. So find the area from 0 to pi. When you're done finding that area, you just times by 2 to get the other side. So this would then be the simplified version of A sub n. That's the simplified version of A sub n. Now, B sub n. So B sub n is 1 over pi integral from minus pi to pi of f of x sine nx dx. Now, if you look at this carefully, what would you notice? You will notice that we're dealing with even functions. If f of s is even, because we're dealing with even, if f of s is even, sine s is odd. I tell you that sine s is what? Odd. Let me write this here. These are the odd graphs. These are the even graphs. So this is even, this is odd. Even times odd will be odd. Even times odd is going to be what? Odd. So let us use this graph because this is an odd graph. So let's use this graph to model our problem, to find a solution. So this graph here is odd. Now see, how would the area be? Remember that this is minus pi, and then this is pi, and this is 0. Now here's the thing. I told you before that the area above the x-axis is positive. The area below is negative. Now since this is above, this will be plus a. Since this is below, this will be minus a. Now let's think of it this way. The reason this part is 2a is because a plus a is 2a. But here, this is a minus a. A minus a is what? 0. So this here, b sub n, is equal to 0. Because the area is going to be 0. Now you can see this is now simplified, right? It's simplified in the sense that we can now tell that, oh, areas, when you have odd guy, that is to say that this f of s was even, this guy is this, so the area of something like this is 0. How does this help us? Whenever we are solving Fourier series and we're dealing with an even function, the only thing we need to find is a naught and a sub n, because b sub n is what? 0. You see why it's now looking kind of, oh, this is a simplification, because if I'm dealing with even functions, I only have to find a naught and a sub n. That's the only thing you need to find. because b sub n will be what? Will be 0. So you see that it kind of makes life easy for us. It kind of makes life easy for us. So these are your formulas. This guy in the box. These are your simplified versions of our formula. Now let's talk about odd functions. Let's talk about odd functions. Do I really want to claim this? I think I'm going to leave it. But then, I'll clean some parts. I'm going to clean, I might even clean this whole page. So let's look at odd functions. So for odd functions, let's start with the first one, a naught. So we have 1 over pi integral from minus pi to pi of f of x dx. So that's an odd function. If you integrate an odd function, what happens? Remember, we've explained it here. I don't think there's need for me to do that again. This is an odd function. So this can be modeled by this. So if this is an odd function, the area will be 0 because this plus a and this minus a will cancel out. So a naught is going to be 0. I don't think I should stress myself with that because the area is 0. 0 times 1 over pi is still 0. Next, a sub n is 1 over pi integral from minus pi to pi of f of x cos nx dx. Now, if you look at this properly, f of s is odd. We're dealing with odd functions now. F of s is odd, so the function we're dealing with is odd. Then this is even. Remember what odd times even is. Odd times even is odd. We did that previously. When the function is odd, you times it by an even function, it's going to be odd. Now again, the integral of odd will give you 0. So this guy here is 0. A sub n is 0. A sub n is 0. Anyhow you want to explain this, it's going to be 0. It's going to be 0. Let me use sin x. Let me use this one for example. Since I'm dealing with these two guys will result to an odd function, so let me model it by this. If I model it with this, the area above x is plus, so this is plus a. The area below it is minus a. So minus a plus a is 0. So that's why this will be 0. Next one, b sub n is 1 over pi integral from minus pi to pi of f of x sine nx dx. Now again, here's the thing. Do you know that there's another way to explain this? Yeah, let me come here. Let me come to this b sub n. There's another way to explain this. Fourier series is the representation of sine and cosine. So you are representing functions in terms of sines and cosine. You are trying your best to see if there is sine and cosine in a function. That's what you're trying to do. If it's encoded or embedded in that very function. Now we know a function is even. If a function is even, there's no way sine can be inside that very function. That is why this is 0. So another way to look at it is, that's why this is 0. When you come to this very part here, f of s is an odd function. There is no way cosine is going to be embedded in an odd function. So that's why this is 0. So that's just another way to look at it. But this one here, this is odd. Sine is odd. So yes, there's going to be a sine. So let's see. This is an odd function. This is odd. This is also odd. Odd times odd will give you an even function, remember. Odd times odd will give you what? An even function. So if a function is even, let me use this one to represent it. If a function is even, for example, we know that if a function is even, this part is positive, this part is also what? Positive. Sorry, this part is negative. Okay, this part is negative. But let me just use this one, please, because you guys might be confused with this, and I would explain when it gets to this. But this side is positive, this side is going to be what? Negative. But dealing with only this one, since it's an even function, if you find one part of it, 0 to pi, you get a. To get the full area, you have to double. So this will just be 2 over pi, so b sub n is 2 over pi. Change the integral, instead of minus pi to pi, that becomes 0 to pi of f of x sine nx dx. So that's just it. As you can see, life is now very easy. So when you're dealing with your coefficient here, and you have an odd function, you are very sure that the function is odd, the interval is symmetric, The only thing you need to find is B sub n. So if you notice that some questions that you are looking for everything, no, but it's disappearing. You're noticing that A naught is 0, A sub n is 0, and you'll just be tired. Why would you not just know and find B sub n? So that is why this is very, very important, that you know when a function is even or when it's odd, and what you have to find. So if the function is odd, you're only looking for B sub n. And this formula can be used as a shortcut for you. Then if a function is even, the only thing you need to find is A naught and A sub n. And these formulas will shorten things for you. So let's go to another video. This will be all for this very video. I believe I've explained everything I want to. So yeah, let's move on to the next video. So I will see you in the next one. Remember to hit the subscribe button, like this video, and share it across to your classmates. Bye.